Okay, we said we'd get back to the ionic solids. Here we are back to the ionic solids. So ionic compounds often have crystalline structures that are similar to or closely related to those unit cells that we talked about earlier. What makes it a little more complicated, though, is that that structure has to accommodate two different ions, a cation and an anion. And depending on the charges, you might have two of one and one of the other. And they also might be different sizes. So that makes it very complicated and interesting. So here, the coordination number is representing the number of close cation-anion interactions. Those lower the potential energy. If we have the cation and the anion more similar in size, they're going to pack together better. And so the coordination number is going to get higher. We have to balance coordination number, charge neutrality, and different ion sizes. So we're just going to look at some examples of this. I just want you to be able to look at these pictures and be able to recognize, what kind of a structure are we looking at? How would we identify the basic unit cell? And how could we identify how many atoms or ions of each kind are in that unit cell? So here we're looking at cesium chloride. So in cesium chloride, the cesium ion and the chloride ion are very similar in size. And so what we have here is the chloride ions are forming a cubic unit cell. So now different colors represent two different kinds of atoms, or ions. So this is a different ion. When we identify the unit cell, we're just looking at one of the ions. So here, just looking at the green ones, that's the cubic unit cell, and then the cesium is going to be stuck in the middle, which makes it look like it's body-centered, but it's not. That guy's just sitting in there, right? So in this unit cell, there obviously is one cesium ion, and there's a total of one chloride ion, because we have an eighth of it at each corner, right? So if I ask you how many ions of each type are in this unit cell, there's one chloride and one cesium. Let's look at sodium chloride. If we didn't have to worry about charge neutrality, we could squeeze a whole bunch of sodium ions in around those chloride ions. But then the charge would not be neutral, and so that's not going to happen. So that causes the sodium chloride crystal to be a little bit more spread out than we might think. So here again, here's the chloride ions in the green. We're looking at the chloride ions to see what kind of a unit cell is this. So this is one face of the unit cell, right? And then it goes over here and over there. So we've got chloride ions in the corners, and we also have a chloride ion where? The purple's in the middle. This is on the face, right? So on the face is the face-centered. And so face-centered, we're going to have 4 ions of each kind. The sodium ions are going to be sitting in between. I don't recommend trying to think or look at the structure and count how many fractions of sodium ions are in there. Just do the chlorides. It's like, okay, chlorides, there's 6 on the faces, that's 6 times a half, that's 3 plus 1 at the corners, there's 4. Well, this is a 1-to-1 ratio of ions, so if there's 4 chloride ions, there has to be 4 sodium ions. When the size difference gets even bigger, then we get some other types of structures happening, and the coordination number goes down a bit. Here we also have a face-centered cubic. So here is one side. So we've got the yellow ones in the corners and one on the face. So there would be 4 sulfide ions, and since there's 1 zinc for every sulfur, then there must be 4 zinc ions as well. But here the zinc ions are not in between like they were in the previous example. Now they are sitting in these tetrahedral holes. That's a subtle point that is just there. It's not that important. Then when you get to 1:2 or 2:1 cation to anion ratios, then things get even more complicated. This is called fluorite structure. And again, just looking at this, so here we have the corners, right? And where is the other bluish one? It's in the center of a face, right? So this is also face-centered. But there's actually 8 of those tetrahedral holes in here, and so we can fit twice as many fluoride ions in here. So looking at the corners, we recognize that those are the calcium ions. There's 4 of those, and it's CaF2, so there must be 8 of the anions in there.